radical review. It sounds much more awesomer than it maybe is. I don't know, actually. Anyway, how I'm going to do these things is that I am looking to simplify them. I'm not looking for a decimal answer. In fact, here I've got my calculator next to me. I'm not looking for the answer of 12.247448871. I'm not looking for that, okay? What I'm looking for is a simplified answer like this. 5 square root of 6 is the square root of 150. So how do I get that if I don't know how to get that? Well, here's what I do. A couple of different things you could try is, one is you could just factor this with the smallest numbers that you can think of to try and make this thing work. I don't know if I want to call it in a pretty way, but the idea is that these are the factors. In fact, they are the prime factors of 150. So the idea is we have the square root of 2. There's that 2. We have the square root, and then times 3 because of that 3, and then times 5 because of 5 and 5. And if you're like, wait, why would you do that? Because if you were to multiply 2 times 3, you get 6. 6 times 5 is 30. 30 times 5 is 150. That's why. And what you do with square roots is you're looking for perfect squares. So that's a perfect square. If you're not sure why, well, it's because it's literally 5 squared, right? So if you see 5 squared, cool, you've got a perfect square. Or if you see 25, why are those both perfect squares? Well, because they both are the same exact number. And so I like to think of it as couples go out on dates. So that 5 goes out. And then single people, this 2 is single, this 3 is single, they stay home and play video games. So 5 square root of 6 is our answer. I told you it was over here, but now I've kind of showed you how that works. So that's one approach you could take. Another is here, let me scooch this 150 over, is don't think of the smallest numbers that could go into it. I mean, think of any number that goes into it, like 10. 10 and 15, that's 150. And then you continue to factor those until you either get some prime factors, which these are our prime factors. And if you're like, huh? Remember these things, prime factors. Or until you get some perfect squares. And then you just do the same thing. So this becomes that right there. And either way, now we have just technically talked about how to do this whole thing. So I'm going to go kind of quickly through this because some of these I think you can kind of do in your head. Like the square root of 20 is really 4 times 5. So that's 2 square root of 5. Because the 4 is a perfect square. And so the 2 is what comes out. Why 2? Because 4 is equal to 2 squared, okay? The square root of 48, that's really 4 times 12. And we could go further with that, and we could do, it is 4 times 4 times 3. And if you're like, wait, why did you do it that way? That's just how my brain started with it. I didn't see that this was really 16 times 3. But I did see that it was 4 times 12. So now here's the perfect square of 4. 4 goes out, and the square root of 3 is left behind. There's our answer for number 3. Now, for number 4, we have 2 separate square roots. They're being multiplied together, so you could go ahead and combine them if you want to be 120. Your other option is the square root of 6 is already simplified because 2 times 3 is 6. Not extremely helpful. But what you could do is kind of go ahead and factor this to where now you're like, well, listen, I have a 2 and a 3 and a 5 and a 2 and another 2. So the square root of 120 is really all of these numbers, right, is 2 times 2 times 2 times 3 times 5. All right, so there's a perfect square. It goes out to square root of, and here's where this one's kind of funky, and some of these will kind of annoy you. 2 times 3 is 6. 6 times 5 is 30. And we're done. The answer is 2 times square root of 30. Seems like maybe something's gone wrong, because surely 30 has a square root. It doesn't. It doesn't have a perfect square, and we actually started our lesson kind of with that today in class, and that we listed off the perfect squares. 1 is 1, so when you take the square root of 1, you get 1. 2 does not have a perfect square. 3 does not have a perfect square, but 4 does. And so what's the point in having in talking about this is that, well, we know the perfect squares like this, and we could keep going. So like now I'm going to kind of cut out some of the middle stuff. 36 is 6, 49 is 7, 64 is 8, 81 is 9, 100 is 10, and so on. I mean, oops, accidentally muted myself. So 121 is 11, 144 is 12, 169 is 13. I'm going to stop there. You get the idea. These are perfect squares. So then when we get something like 30, 30 is clearly caught between some perfect squares. So it's going to have to be composed of perhaps perfect squares. But 30 is not, because 30 is 2 times 3 times 5. Make sense? All right, number 5. With number 5, what we've got is we've got a coefficient of 7. So he's already outside the party, so to speak. You know, here's the party is inside the square root. 121 is 11 squared. So here's what happens. It goes out and joins the 7. How does it join it? It multiplies. So 7 times the square root of 121 is 77, because of 7 times 11, okay? We talked about how this is the index, and an index, we haven't seen one of those yet. There was nothing here. There was nothing here or here. Why not? Because a square root implies that we're looking for perfect squares, right? And so it's kind of an invisible 2. It's not kind of an invisible 2. It is an invisible 2. So now we don't have an invisible 3. We are now looking for perfect cubes. So here I'm going to write like cubes, like x cubed. And then just to kind of back up, to reiterate what I was just saying, perfect squares are like x squared. Okay, so this problem actually becomes really simple, because the cube root of 27 is really 3 times 3 times 3, or it's the cube root of 3 cubed. And so we are looking for perfect cubes. So what happens is 3 goes out, and that's it. And if you're like, wait, how is that it? Well, just like over here, when I take the square root of 25, it's just 5. There's no more square root symbol, because I'm done with it. Same thing here. There's no more cube root symbol, because I'm done with it. Okay? Number 7, you can essentially break this up into the square root of 9 over the square root of 64, and then we would get 3 over 8. Pretty simple there, right? This right here says I have 3 of this. I have 9 of this. I have -4 of this. Well, check it out. That's square root of 3, that's square root of 3, that's square root of 3. They're all like terms. So, for example, if I wrote this you would go, oh, well, that's 12x minus 4x, that's 8x, right? You'd say, boom, 8x, and you'd be right. Well, guess what? This is 3 square root of 3 plus 9 square root of 3. That's 12 square root of 3. 12 square root of 3 minus 4 square root of 3 is 8 square root of 3. 8 square root of 3. We're done. Oh no, we don't have like terms, but maybe we could. So we just have to simplify each piece. So that red one cannot be simplified. The square root of 5 doesn't have a perfect square. This blue one, on the other hand, the square root of 36 is just 6. So it's 6 times 3 is 18. This green one can be simplified. Let's do this. We have 80. Oh, my pen got giant all of a sudden. 80 is really, let's see, 10 here. I'm okay, I'll do it this way. I kind of have a preference for this, but I grew up doing like the tree thing. So here, let's do 2 times 40 and 2 times 20 and 2 times 10 and 2 times 5. Why do I prefer this? It's kind of easy to divide by 2, you know what I mean? So there's a perfect square, there's a perfect square, he stays home. So it's not just 2 goes out, but 2 times 2. So we get 4 going out, and look, there's already a 2 out there. So let me slow down for a second. These 2 2's will separately go out and multiply to become 4. This 4 will join this 2 to become 8 square root of 5. Why 5? These 2. Okay? And then in that situation now we've taken care of all of the factors of 80. Okay? And then I'm just going to bring this one down here. 5 square root of 5. We're adding that 13. So check it out. Just like the previous one, these 2 are like terms. So I know I have drawn a lot. I'm going to actually put my answer down here in this box. For number 9 is 13 square root of 5 plus 18. That is the final answer. All right, this one might be intimidating looking, but again, it's just like terms. We have 3 of these, 10 of these, and negative 2 of these. They're all like terms. So let's just combine them. 3 plus 10 is 13. 13 minus 2 is 11 times the cube root of 5. All right, square root of 9, that's 3. Square root of 100, that's 10. That's it. Square root of 4, that's 2. Square root of 25, that's 5. That's it. All right, the good times have come to an end. Square root of 20 over square root of 27. I say the good times have come to an end because square root of 20 is 4 times 5. Square root of 27 is 3 times 9. Now, it hasn't truly come to an end because this is a perfect square of 2 times 2. So the 2 pops out like that. This is a perfect square of 3. So the 3 pops out. And now we are done. So it's kind of a funky looking answer, especially, 2/5, not bad, but 2 square root of 5 over 3 square root of 3, a little uglier. All right, 14. I'm going to tell you, these are common square roots that are not perfect squares. And what I mean by that is, well, let me show you the answer, and then I'll back up and give you the in-between part as to why I say that. So there's the answer. And I say that the square root of 8 shows up, it seems like it shows up all the time, and it's 2 square root of 2. Why is that? Well, because it's the square root of 4 times 2. This 4 goes out, right? And then the other 2 stays home. Up here on top, we just did it. It's the square root of 3 times 9. The 9 goes out, and that 3 stays home. So this entire answer is not super common, but these guys individually are kind of common. Okay, this isn't our first instance of multiplying. We multiplied on number 4, but this is our first instance of distributing. So here's how we distribute. They put the square root of 6 on the back end. Not 100% sure why, doesn't really matter. We're going to distribute it to that and get the square root of 12. We're going to distribute it here and get the square root of 18. So can we simplify it from there? Yeah, we can. Square root of 12 is really 4 times 3, so perfect square can go out. The square root of 18 is really 9 times 2, and we have a perfect square that can go out. So we end up getting 2 square root of 3 plus 3 square root of 2. I think I see what they were getting at here. They were wanting to try and trick you into combining these, but this is the square root of 3. This is the square root of 2. These are not like terms. So this is your final answer here. Number 16, distribute again. So we're going to get the square root of 16 plus the square root of 18. That feels off, but, that feels off because that's wrong. That's the square root of 24. Okay, let's simplify. The square root of 16 is really, that's a perfect square. It's 4 times 4. So this is just 4. And the square root of 24 is really, let's see, it is 6 times 4. That's a perfect square. It jumps out to be 2 square root of 6. And we are done. And if you're like, wait, what about the square root of 6? Some of them are going to feel like they can continue, but they cannot. 6 is 2 times 3, no perfect squares. Hey, it's our first group with a variable. And we are still looking for perfect squares, okay? And you might think, well, that's kind of tough. I don't have a perfect square there. You do. X squared. That's a perfect square of x squared. Let me give you a slightly simpler answer. X squared is a perfect square, okay? It equals x times x. It's just like the concept of 25 equals 5 times 5, right? So don't get too confused on this one. The idea is it's like we have 2 x squareds. I mean, that's what we said here. So x squared goes out, okay? And then the square root of 64 is 8. So here's the final answer. It is 8x squared. The square root of 64x to the 4th is 8x squared. And I haven't said it yet, but here's one way you can check your answer. Square this. If you were to square it, you would get 64x to the 4th. And that's what we had. If any of these, if you've taken the square root, if you then square it, you should get the original. So like the square root of 48, is it this? Well, let's find out. Let's square it. So what that means is you would have 4 square root of 3 times 4 square root of 3. 4 times 4 is 16. Square root of 3 times square root of 3 is 3. And 16 times 3 is 48. So yeah, we did that right. I know I haven't said it up to this point, so hopefully you didn't necessarily need it up to this point, but now there you go. All right, square root of xy cubed times square root of x cubed y. What's going to happen is the x's are like terms, so we get x to the 4th, and the y's are like terms, so we get y to the 4th. Now, we are looking for perfect squares, right? So if you want to think of it this way, x to the 4th is 2 perfect squares, and y to the 4th is also 2 perfect squares. So what will happen is That's 1x. That's 1x. So 1x plus 1x, that's x squared that pops out. That's 1y, that's 1y. And in fact, wait, why is it 1y? Is because if I just had the square root of y squared, that would be y. So there is your final answer on 18. 19, we'll have the square root of x on top. We'll have the square root of y to the fourth on bottom. If you see it, then what you could have done immediately is just have written y squared, and you would be done. Leaving the square root of x on top is perfectly fine. The square root of 50 divided by z to the fifth. So we're going to break this up to the square root of 50 over the square root of z to the fifth. Now, we're about to encounter something on this problem that we haven't encountered thus far. Don't worry, it will be relatively simple. But first thing is, let's deal with the 50. That is 25 times 2. So obviously that is a perfect square of 5. So this turns into 5 square root of 2, yeah? This is 1, 2, 3, 4, 5 z's. So we have 2 pairs. Z squared is going to pop out. And the square root of z, that fifth one, this fifth one, stays home right here. And now for the part that, I said was unique to this one, at least thus far, is that we are going to simplify this. You might think, well, didn't we simplify it? But so I've kind of joked in class that we don't want to do not finish, or perhaps you are not finished with negative exponents. And then you're also not finished when you have radicals in the denominator. Okay, so we have a radical in the denominator. So what we're going to do is rationalize this. So that's a word. Obviously, it's a word, rationalize. So what that is going to do is we are going to multiply this fraction by the square root of z over the square root of z. You could kind of think of rationalizing like coming up with a common denominator, in that, hey, you're gonna, remember common denominators, we couldn't just add that, so we had to multiply this by 3 over 3, and we had to multiply this by 2 over 2. And what was the point of that? Because isn't 3 over 3 just 1? Yeah, it is. But when we multiply this by it, obviously we end up getting 3/6 plus 4/6, and then, we could just add and get 7/6, right? So here, similar thing's going to happen. This is just 1, but when we multiply it over here, what we get is 5 square root of 2z. If you're a little confused on why that's not a z, remember it was 25 times 2 right here. So that's a 2, not a z. I try to make my z's very pointy. Next, on the bottom, what's going to happen is we get z squared times z. Now, hang on. Actually, let me back that up. We do get z, I promise. But let me show you the in-between step. We would get square root of this blue z right here, this blue z, the original one, and then this green z, this one right here that we'd said, hey, let's multiply by. And what's going to happen is now that's a perfect square. And so we end up getting that on top, it's still 5 square root of 2z over, but this perfect square. So a z pops out, and it's going to multiply that z squared, and we get z to the third power. So this was kind of a funky one, especially this feel right here. That felt kind of funky, right? And just so you know, we could have, if we wanted to, have rationalized it right here, and we could have multiplied this whole fraction here by the square root of z to the fifth. I think that would have caused random extra bits. And if you're like, extra bits, what the heck do you mean? Well, we would have had z's in the numerator. And if you're like, well, we do have a z's in the numerator. Yes, that's true. But we would have had z squared up here. And what would have happened is I believe there'd been some canceling, So I say do some simplifying first, then rationalize. That's my story. You could try it your way if you want. Not that you said anything about it being your way. You get the idea. All right, we have 5 times the cube root of 432, a to the 5th, b to the 6th. So just because I feel like it, I'm going to deal with the a's first. I have 1, 2, 3, 4. There are 5 a's, and if you're like, what the heck is that? Why is he writing these little things? I'm just kind of visualizing mentally that that's what I have. There is a cube, and that's what would be left over. How many cubes do I have here? I have 1. So that 1 is going to go out. So this 5 is already out. 5a b to the 5th. I have, b to the 6th. Well, so I would have 1, 2, 3, 4, 5, 6 b's, b. And I'm pretty sure you agree that, hey, look, there's a cube. We have 2 cubes. So what's going to happen is that cube comes out. And then what I'm going to do is just go ahead and write that I have left over the cube root of 432 a squared. And I'm doing it that way just so that now I can kind of mess with 432. I don't know my cubes very well, so I'm going to have to come over here and be like, okay, really how I'm going to approach this is 432 divided by, I know it seems stupid, but I'm going to divide by 2. So I will get 200 and what is that? 16? 216. And I can divide that by 2, and I get 108. And I'm starting to think, okay, this is going to work out. I get 54. I can divide that by 2, and I get 27. And this is 3 times 9, and that's 3 times 3. So check it out. I am looking for cubes. There's 1 cube. Here's another cube. And this guy is left behind. And if you're like, what the heck is going on? Apparently, 2 times 2 times 2 times 2 times 3 times 3 times 3 is 432. And if you're like, okay, 8 times 27 times 2, that's a perfect cube. 8 is a perfect cube. 27 is a perfect cube. So again, what's going to happen is this is going to go out. This is going to go out. So 2 and 3 go out. That is 6, by the way. 2 times 3 is 6. Hang on. Am I doing that right? Yep, I'm doing that right. So what's going to happen is this guy, now it's 5 times 2 times 3. Where am I getting the 5 from? That 5. Not some other random mystery 5. So 5 times 2 is 10. 10 times 3 is 30. We get 30 AB squared. Let me zoom out to go grab this 2. Remember? Times the cube root of 2a squared. Woo. That felt like a lot, right? But there you go. Now they return to a much easier, faster one. The square root of 144 is 12. The square root of x squared is x. Like 1,000 times easier, the number 21, right? 3, 4, 5, 6. Okay, well, again, I'm going to have to do like a little factor tree thing. So 3, 4, 5, 6, that can be divided by 2, right? So I guess that's what we'll go with. 17, 28, and divided by 2. And you know what? I'm honestly, I'm sitting in my car because my son is at basketball practice right now. Kind of wish I had my calculator. But here we go. Let's keep going. 17, let's see, we can divide that by 8 and 864, I believe. Divided by 2 is 4. 32. Divided that by 2 is 2. 1, 6. 2 is 108. And look, we're approaching the same thing we just did. This is 54. 2 times 27. And this is going to end up being 333. So I changed to purple because I'm like, hey, look, I'm going to have a triple there. I have a triple here. I say triple, I'm meaning cube, right? So we have one cube, another cube, another cube. So a 2 is going to go out, a 2 is going to go out, a 3 is going to go out. 3 times 2 times 2, that's 2 times 2 is 4. 4 times 3 is 12. So, and then don't forget this lonely 2 that's going to stay at home. So 12 is going to come out. 12 cube root of 2. That's the answer. And if you're like, hey, how could we double check that? Cube 12. So 12 times 12 is 144. Multiply that by 12. And let's see, you'll get 288,01448. Let's see, 1728. And then check it out. There's 1728. And if we multiply it by another 2, we get 3456, which is what we had originally. So I just basically checked my answer to go, yep, I'm right. 24 is the square root of 81 times q to the 6th. The square root of 81, 9. The square root of q to the 6th, q to the 3rd. Again, about 100 times easier. 25, the square root of 75. Well, 75 is 3 times 25. And the square root of 25 is 5. And then now here's an example, like back up here, I was drawing little pictures. I was doing that. I don't want to say like, oh, I was doing it for you, little buddy. But I kind of was. So let's graduate now to the more awesomer approach. Since we are doing a square root, remember, there's a invisible, oh gosh, what's the word? I'm in the middle, like I said, I'm out in my car, so I have to think of the word. Anyway, can't remember at the second. We're to divide by 2, and we would get 9. So guess what? Z to the 9th. That's what you'd get. If you had any left over, and if you're like, what do you mean left over? Well, let's pretend it was 19. When you divide that by 2, it doesn't divide evenly. You would get, let's see, you get 9.5. Or think way long time ago when you divided as a kid, you would be like, oh, well, listen, that's 9, that's 18, and you would have a remainder of 1. So there would be a z left over if we had had 19. We do not, though. Okay, so now we're starting to do a little bit of solving. This is a little bit different if you're not familiar. So what's going on is this x is being square rooted, and I live in the world where PEMDAS is how I think about things. So can I do what's inside of my square root? No, well then parentheses are done. Guess what? This whole thing is an exponent. Which exponent? It's to the 1/2 power. So here's what I'm going to do. I'm going to square that, And what happens when you have a power to a power is this just becomes x. So I'm going to square my square root, and if I do it to one side, I have to do it to the other. I end up getting 2x plus 7 equals 25. And now this is a super easy problem. I subtract 7. I divide by 2. I'm done. That's it. 27. The square root of 1 minus 2x is equal to negative 4. Again, I am going to square both sides. And I get 1 minus 2x equals 16. I add 1. No, I don't add 1. I subtract 1 from both sides. I get 15. I divide by negative 2, and I get x equals negative 7.5. Now, something I want to point out. If you're somebody who likes to plug in and check your answers, you would end up getting the square root of 16. And does that equal negative 4? I think you are going to say no. But here's the thing. Technically speaking, the square root of 16 is literally both positive and negative 4. So does that equal negative 4? Yes. And if you're like, wait a second, I don't remember ever hearing that. So there's something called a principal root. The principal root is the positive root. But think of it this way. What's 4 times 4? Definitely 16. What's negative 4 times negative 4? Also 16. So you see how that works? Maybe you do, maybe you don't. Let's see. The cube root of 2187. Did I have anything like that back over here? Oh, man, I wish I did. So 2187, let's see. That is divisible by 3. So let's get crazy. 2187. If I divide that by 3, I get 7, and I'm going to have to do a little bit of, wait, is that, yeah, that's divisible by 3. 7, 2, that's, yep, 729. Okay, I think this is going to work out nicely. That's divisible by, also 3. I was going to try 9, but when I do it in this fashion, I prefer to just go with small prime numbers. So anyway, divided by 3, let's see, we get 24 and 3, and we can divide that by 3, and we get 81, and I think you'll see where this is going. That's 27 and 9 and 3 and 3. So check this out. This is 3 to the 1, 2, 3, 4, 5, 6, 7, 3 to the 7th power. So let's zoom in here. The cube root of 3 to the 7th power. Well, kind of like we did up here where I was like, hey, listen, we can just divide that by 2. Well, here, since it's a cube root, we could divide this by 3. And, I mean, not that you would have known that 2187 is 3 to the 7th power. But what happens is, let's see, 1, 2, 3, 4, 5, 6, 7. You would get 1, 3. You would get 2 3s, and then a lonely little 3 would stay at home. So we actually could verify that down here. 1 3 goes out, another 3 goes out, and this one stays at home. So the answer is 9 cube root of 3. Wow. Another solving one, we're going to square both sides. We get 3x minus 5 equals 25. We add 5 to get 30. X is 10. Nice. 30. That's the square root of 5. That's the square root of 5. I have 7 square roots of 5. How did I get that? Because I have 3 of them plus 4 of them. That's 7 of them. Okay, so if you're waiting for me to do these others, I've decided I'm going to stop here. Not because, I'm tired, but I think I've given you an incredible foundation from all of these in order to tackle these last few. So if you have questions on those, let me know. Otherwise, see ya.